OK, so up next, we have Homomorphic Encryption for Retrieval of Witness Data by Semir Menon at Bliss.
OK, can you go back? Good morning, everyone. I'm Semir Menon, and today I'll be giving a talk about using homomorphic encryption to privately retrieve data. So I want to anticipate the first objection to the talk, which is, this is zkParis, and it does not say zero knowledge in the title of the talk. It doesn't even have a Z. So what am I doing here? I want to think like I'm an emissary from a different branch of cryptography. And I think that homomorphic encryption sometimes makes sense in a lot of contexts that you're using zero knowledge. And so I'll ground like what we're doing today or what I'm explaining in an example from a lot of common zero knowledge applications. So this is one where many people in this room are probably very familiar with, which is proving set membership in zero knowledge. So imagine that you want to prove that you're a member of some set without revealing your identity. We know there's a lot of fancy ways to do this. You can use polynomial commitments, you can use a Merkle tree, but the reason we want to do this is it comes up often in multiple contexts. So it's not just, it is a useful primitive in a lot of things, such as proving that you should get a badge if you have a certain number of assets, proving that you have like a receipt for a cross-chain bridge to kind of get your funds on the other side, and even in voting, right, to prove that you're a member of the set of people that's allowed to vote. So we're gonna work through an example of proving set membership in zero knowledge, the super old dumb way. Oh, I guess the lines are missing, but you can probably imagine the Merkle tree here. So we're not using polynomial commitments or anything, but yeah. So let's say we're trying to prove that we have membership in some set committed to by R. Just really verbosely, like the statement we're trying to prove in this example is basically, I have some secret X. It corresponds to some kind of public version of X. So I've chosen like a key pair. So I have some secret key X. And this corresponds to some public key Y. And basically, my proof is going to consist of the statement, I know values that hash to the root R. So R is some public value. And I'm trying to prove in zero knowledge over X, Y, and P. I'm trying to prove that I know some X. And the key is like I don't want to reveal which X I am. So which leaf node I'm proving membership for. So to produce this proof as a client, I need X, Y, R, and P. So that's the private key, the public key, the root, and this P, this Merkle proof, which is like the set of sibling nodes on the path from my leaf to the root. And the thing is, gathering these for the client before they can compute the proof locally is kind of a process, right? So in many applications, like the client already knows X and Y. So like for voting, I know my private key, and I also know my public key. And R is a kind of public value that is safe to retrieve, basically. So it doesn't reveal anything about my secret. But there's a complication for P. So I need to get these nodes in the Merkle tree that that are basically siblings along the path up to the root. But the problem is, these sibling nodes are, if I just kind of naively fetch them, I will reveal which path I'm actually about to do a proof for. That's kind of a little bad, So let's think about like what are our options here. So firstly, if we just if I'm on a light client, right? And I just send my RPC get storage at calls to my full node that's serving me, they're going to immediately be able to tell which path I'm constructing a proof for. And that kind of defeats some of the purpose of trying to do the whole thing in zero knowledge. There are some other options. So another thing we could think about doing is using like Tor or a VPN. So we could try to hide our network identity, like our IP address. But that basically kind of doesn't obscure the association of the fetch. So if log n get storage at calls all come in at the same time, it's pretty clear that I'm proving for some Merkle path, and it's clear actually which path. So if later, immediately you publish a transaction to the chain that does something, I can probably infer, which identity kind of put forth the transaction. So IP address obfuscation is kind of imperfect. And then this is actually the solution, at least in my experience, most people are still doing today, which is another option is to download the entire tree. So if you just download the whole Merkle tree, then nobody knows what path you're trying to get. But of course, this doesn't work as soon as the tree is big. So if the tree is getting really large, like if it has, let's say, 1 billion entries, it's not going to work to just download the entire one. It's going to be gigabytes, right? So what are your options here? In this, and I'll caveat here, sticking with this idea that we're doing set membership proofs with Merkle trees. What are our options? So what we want is to get the Merkle proof. The Merkle proof is the path up to the root of sibling nodes. We want to get this proof without revealing which path we're getting the proof for. So there's actually a well-known problem in cryptography. This actually predates even homomorphic encryption, called private information retrieval. It's a kind of simple problem to state, but maybe hard to solve. So the problem is basically you have a database with n items. The client wants to get an item at a specific index, and the server should not learn which item the client gets. And the naive solution to PIR is always to just download the entire database. And the premise of PIR as a cryptographic problem is, OK, can you do better than downloading the entire database? And we actually can do better. We can do a lot better. We can actually do optimally. We can upload log n data, and we can download constant data. So we have solutions for PIR. And just to see exactly what I mean by PIR would solve this, basically what we'd be doing is PIR at every level of the tree. So at the bottom leaf node level, we want to fetch exactly one node of these 4. And so we want the sibling node of our target node, the orange one there. And then we would do that for every level. So we need to do log n PIR queries. So the title of the talk had homomorphic encryption in it. I still haven't gotten to it. So where does homomorphic encryption come in? Basically, the idea is to actually do PIR, to instantiate it, to have the server somehow be able to give you this information without learning which item you're taking. We need this other cryptography called homomorphic encryption. This is not a long enough talk to just explain all of homomorphic encryption, so I won't try. But basically, homomorphic encryption is a kind of encryption that lets untrusted parties compute on encrypted data. So the idea is at a very high level, you can add and multiply ciphertexts, and the ciphertexts that are, after you add them, will encode the addition or multiplication of the plain text. Homomorphic encryption has been around for a while. Seminal work kind of outlined it about, I guess, 15 years ago. But it has a pretty bad reputation. The generic slowdown that you get when you try to run a computation in HE is still 1 million. It's actually something I've always been jealous of ZK for, because things have gotten a lot better for ZK, and at least verification is very fast. It's not like that for homomorphic encryption. We still have very large slowdowns. There's some good news, which is for a very specific kind of circuit, a very specific kind of computation you want to do on encrypted data, we can do much better than 1 million. Basically, we can do a lot better. And the specific application is if we do this PIR thing using homomorphic encryption, we can go really fast, and we can be really efficient. As a side note, I'll say it is based on lattices. So fun fact, it's also post-quantum cryptography. It's also, in the event someone builds a quantum computer, we will be using something like this. At this point, people are usually okay, I really just want to know how it works. Can you explain? So I will explain roughly, how do we actually get PIR from homomorphic encryption. So homomorphic encryption, maybe I could believe that works, but how do you actually use it to privately retrieve data? The basic idea is you have the client encrypt like this large vector of bits, where basically they're all 0 except for 1 in the position of the element that the client wants to retrieve. And the client encrypts all of those and uploads them to the server. And they encrypt them using a homomorphic encryption scheme. So then the server can do this big dot product, where it takes the entire database and the query, dot products them, and sends back the result. So basically, you'll get a 0 for all the items you don't want, and you'll get a 1 times the item you want. And you'll send that back to the client. This is kind of illustrative. Like, we don't actually upload order n ciphertext, and we do more complicated things than this. But that's kind of like the gist of how it's possible using homomorphic encryption. Yeah, I have like a blog post that kind of explains more about exactly how this works. I want to say a little bit about, okay, so like, can you use this? So the speed at which the server processes the database is really important. So PIR, for privacy reasons, you can imagine, the server generally has to process the entire database for every query, right? It needs to touch every item in the database, because if it didn't touch an item, you would kind of know that the person wasn't retrieving that item. So you have to do this linear scan over the database for every single query you make, which sounds like a lot. I guess the good news is we've done a really good job of making that linear scan very fast. In fact, it's so fast that it's as fast as memory bandwidth. So like, as fast as you can read the database into memory, that's how fast we can do this PIR computation. So that means like at 10 gigs a second, which is like a rough per CPU memory bandwidth benchmark, you can, for let's say billions of Merkle trees, answer a PIR query in less than a second. So we think this is like, or I think this is like finally practical. This has been many years in the making, but it's finally like possible to kind of use this in the real world for like this Merkle tree thing, and actually achieve privacy at very low cost using homomorphic encryption, which honestly has not really been done yet by anyone. So I think it's very exciting. This is like a much stronger kind of level of privacy than you would get if you just like use 2 or 3 different full nodes, or use Tor, or download only a Merkle subtree. Like, this is a very strong level of privacy, right? You reveal absolutely nothing about which path you're proving for to the server. My big asterisk, especially with this audience, is, okay, well, we know there are other ways to do set membership proofs that are maybe a bit better. So if you use a polynomial like set membership proof, you don't actually need to do this, right? You don't need to fetch this path to the root. So that's definitely kind of something to consider. Like, it's like maybe an underrated advantage of the polynomial set membership proofs that you don't need to gather this kind of, let's call it auxiliary witness data. But it leads to a broader point, which is, well, if you're using ZK to put all this stuff on chain and make it private, then if every way that everyone accesses that data is like not private, you might just like defeat your purposes. So I think like a little maxim I think about is like, yeah, whenever you're building on-chain privacy, and you have people using light clients, the question to me obviously becomes, okay, does the RPC node provider just see everything? And are we just kind of throwing our hands up at that? And I think that there's finally cryptography that can solve this problem instead of kind of more social solutions, or kind of just trusting the RPC node provider. And so I think PIR using homomorphic encryption is like a really cool tool for that. Yeah, I won't say it's like a silver bullet. I think it's still good to use other like defense in depth kind of good practices. Like, you should also try to minimize network leakage, or use like heuristic defenses like using more than one full node. But yeah. And I'll say another thing, which is, yeah, the costs are really low. That's like the headline. I think if you want to like try this or see this, we have projects today that use this for or have tested this for Merkle trees with like millions of nodes. So it's like practical. I co-founded a company that just works on basically making this practical, especially for light clients. So yeah, that's it.
Awesome. Thank you, Samir. Do we have any questions for Samir?
Yeah, thanks a lot. Very nice talk. So in PIR, you usually need to give the client certain hints for the database, basically some pre-computation values that you deliver, right? And those depend on the state of the database when those were computed. And usually when the database changes, you have to recompute that. Can you speak to that for a moment? How your solution looks?
Yeah, absolutely. Yeah. So definitely in academic literature, the way we benchmark everything is we have an offline phase where you can shove all the hard stuff, and then you can just say the online costs are very low. So one of the things that gets pushed to the offline phase is the hint. There are schemes that don't rely on a hint. So the scheme I co-authored doesn't. So there's no hint. There's no client download on database update. So the scheme is Spiral. But you pay for that. I mean, the bandwidth, the processing time is kind of longer. But so there's a trade-off in schemes.
Yeah, very good talk. I have a couple questions. One of them is there a particular reason why you do the PIR layer by layer? Because the lowest layer already has n entries, so it seems like you could just do one PIR for all the n different paths.
Yeah, so there's actually a funny trade-off there. So we don't actually do it layer by layer because, of course, the top layers, like you say, are really small, right? If we instantiate all the paths, then we've actually made the database grow in size, right? So remember that the response time is linear with the size, so it's actually kind of a bad trade-off to kind of instantiate every path because then we're paying n log n. So we do exactly something in the middle. So the client downloads a cap, the top, whatever 11 layers of the table, and then they download kind of subtrees of the Merkle tree.
Makes sense. And then I guess my other question was whether the same thing or your protocol, or have you looked into the problem of, I want to know, one other application of this is knowing, did a transaction for me arrive, right? This is more, is it called attribute something based PR or something where I have a public key and I want to know all the data that is associated with it. Do you think you could do that with this approach, or?
Yeah, there's actually really amazing work on this called oblivious message retrieval. I think it's sponsored by the Zcash Foundation, actually. It's exactly this. You need this public key. If you do it generically, with FHE, it's insanely expensive and slow. The paper comes up with a way to make a specially designed tag that you apply in addition to the normal transaction signature that makes it easy to filter on. So you have to do kind of the challenge with that approach is you have to change something about the protocol. All the submitters of transactions now need to add this tag, but then it is easy to do oblivious retrieval.
Okay, thanks.
The solution that you showed on the slides, it looked to me like you only needed homomorphic encryption as opposed to fully homomorphic encryption. Is that correct for the actual solution as well?
Yep. That's why I don't say FHE. So yeah, FHE is the one with the million-x slowdown today. So I don't use that. So we use, I guess the word has changed a bunch, but yeah, it used to be called leveled homomorphic encryption. It just means homomorphic encryption that can evaluate circuits of a bounded depth, bounded a priori before we do the encryption. Yeah. So in this, So in the naive scheme I show, no, it's just linear. So with just linear, you can get a root n like communication. So you upload root and ciphertext. You respond with root and ciphertext. If you want like better communication, then you need ciphertext multiplication. So we do use ciphertext multiplication because it gets you much smaller queries and smaller responses.
Okay, more than one, I guess.
Yes.
Okay, one last question for me. It's so there are other alternatives to fully homomorphic or fully homomorphic encryption, which are more towards the oblivious transfer land. Do you have an idea of how do they compare and why you wouldn't go for the oblivious transfer idea?
Yeah, so oblivious transfer is basically PIR plus the guarantee that the client's not allowed to learn more than one item. So oblivious, like if you have a 1 out of 2 oblivious transfer, the key like guarantee is that the client's not able to learn both items in the 1 out of 2. They're only allowed to learn exactly one item. PIR is like, doesn't make that, I guess, security guarantee. So the client could learn information about, in theory, all the items. If they... Yes, so oblivious transfer is kind of like it's like a stronger problem. If you have oblivious transfer, you automatically have PIR, yeah.
Approach is not useful for you guys?
Yeah, it's just much slower. So if you just like for n items on a single server, doing oblivious transfer is like slower than doing PIR. Yeah. So like if you have like 10 gigs of data and you want to like oblivious transfer like, I don't know, like 1 kilobyte from it, you have 1 out of 1 million or something. So that oblivious transfer is very expensive.
128 Diffie-Hellman operations. And then you use oblivious transfer extensions and you should be able to do it.
Yeah, so like the, sorry, say that first part, 128.
Talk about this offline.
Yeah,
It will be
okay.
interesting.
Yeah, no worries.
Sorry.
Thank you.
I'll just